All right, so yesterday we talked about these double replacement reactions. I'm in the wrong chapter, aren't I? Yeah, we're supposed to be chapter 10, right? Yeah, we're supposed to be chapter 10. Sorry about that. Okay, there we go. Okay, so we talked about chemical reactions, we talked about balancing equations, and then we talked about these precipitation reactions. So again, a precipitation reaction is where you take two compounds. All right, in this case, we are taking sodium iodide. So we're taking sodium iodide. I can't get an option there. Enable editing. There we go. There we go. All right, we took sodium iodide and reacted it with lead nitrate. All right, so the equation is sodium iodide, and these are aqueous reagents or reactants. We talked about what aqueous means yesterday. It just means it's dissolved or ionized in water. And then lead 2 nitrate, which is also aqueous. Okay, and the products, based off of what we have here, is lead iodide. All right, now that is the precipitate, so that's a solid. That is turning into a solid, and we're going to talk all about this today. I'm just trying to show you this example. And then you have sodium nitrate, which is also still in the aqueous form. See how they show it in the ionic form? So it's still aqueous. So this is the equation. So sodium iodide plus lead nitrate, and we have two clear solutions, and we mix them together, and we get this yellow solid right here starting to form. Okay? So the question is, what is the yellow solid? How do we predict what the yellow solid is? And then how do we predict what happens with these compounds? All right, and it's what's called a double replacement reaction. So let's go to that real quick. So here is a double displacement reaction. It doesn't matter how you say it, either a double displacement or replacement. You can use either words. Okay. Basically, what the reaction is, I don't know if they. Reaction is if I take compound AB, okay, whatever AB is, so in this case, lead nitrate, and I react it with compound CD, so our C is our cation, our B is our anion, all right, so here's my cation on A, here's my cation on C, here's my anion, no, let's make the CD, not CB. What a double replacement reaction is, they basically swap each other, okay? So that the cation here pairs up with the anion over here. So we form AD. And then the cation here pairs up with the anion over there. My D's look like B's today, apparently. AD. And then my C pairs up with B. Okay? So the lead pairs up with the iodine, okay, to form lead iodide. And the sodium pairs up with the nitrate to form sodium nitrate. All right. If you're wondering about all the numbers, well, that goes back to the charges, right? This lead has a 2+ charge. That lead has a 2+ charge. How do we know? Because nitrate has a 1- charge from the polyatomic charge sheet. I know. So lead is one of the post-transition metals, so we can have more than one charge. So this goes back to naming again and writing formulas. So since my nitrate has -1 and I have 2 of them, that means my lead has to have a 2+ charge. Okay, and then the sodium and the iodine, sodium always has a +1 because it's in the 1A row. Iodine has a 1- because it's in the 7A row. So the lead pairs up with the iodine. So the formula would be a PbI2. That's to get PbI2, because you need 2 iodines for every lead. And then NaNO3, because my sodium has a +1 and my nitrate has a -1. So NaNO3. So you have to be really good at making sure you know how to figure out the charges on all these ions. Okay, so make sure that you are still good at that and that you understand that, because you have to be able to figure out what the formulas are in the product. Then they balance the equation. All right, so if you wanted to, you can go back and balance the equation. All right, since there's 2 iodines, you have to have 2 iodines, 2 sodiums, 2 sodiums. You already have 2 of the nitrates. Okay, so that's basically what a double replacement reaction is. All right, so what I want to do is I want to just kind of do a few of these problems. You see, and I'll talk about this chart in a second. Let's just do a practice problem. Let's say we take calcium chloride and we add it to, let's say phosphoric acid. Okay. Why don't you guys show me what the 2 products should be? So this is a double replacement. Write the formulas write them in the correct formulas. If you want to balance the equation afterwards, you can go ahead and balance it. You don't really have to in this case. In this case, I just care that you know what the 2 products are. But if you want to go ahead and balance it, you can go ahead and balance it. All right, I'll give you guys a few minutes. A trick how I do it, because you guys are going to have to do this eventually too. What I do is I write down what the 2 ions are that makes up this molecule. All right, so let's drop down here. So a calcium, and a calcium I know is in the 2A row, so it's going to have a 2+ charge. And then it also is a chloride ion, because Cl has a -1 charge. Okay, now that 2 does not come down here, because that 2 is not part of the ion. What you have to think to yourself is, if I take calcium chloride and I throw it into water, what are the ions I form? So a good visual of this is you form a calcium ion and you form 2 chloride ions. And all you're doing here is just writing what the ion is, not how many of them there are or anything like that. If you want to, you could. If you want to put a 2 right there to balance it, that's totally fine. But like I said, right now I just care about you understand what the ions are and how you switch them. I don't care about the on the balancing. Okay, so I want to make sure that you understand that this is your ion. This Cl- is the ion. I'm going to erase the 2 for right now, because I don't care if you know it or not right now. I mean, I care you know it, but right now we don't have to have it. Just basically all I'm doing is writing what 2 ions this is composed of. So if I were to dump it into water, what would happen? All right, same thing for here, H3PO4. When I throw that into water, all right, I get H+ ions. All right, now I get 3 of them, but again, I don't have a 3 as a subscript. All right, it's an H+ ion. And then the PO4 is a phosphate ion. I form a phosphate, a PO4 3-. Okay, so this little equation I have here is just basically showing what ions this turns into and what ions this turns into. So all I'm doing are the ions. I'm not showing the 3 again, is because I have 3 of these H+ here. I have 3 H+. Okay. Okay. So now I have the ions it's composed of. Now I take the calcium and I pair it up with the phosphate. So since calcium has a 2+ charge and phosphate has a 3+ charge, you crisscross the charges. Your formula should be Ca3PO4 2. All right. And then the HCl, hydrogen is my cation, pairs up with chlorine, which is my anion. I form HCl. So those should be your 2 products that you form. Any questions? Is that what you guys got? If you have a question, just unmute yourself and go ahead and ask it. It's easier that way. But I want to make sure you understand how this all comes about. Now, if you wanted to balance it afterwards, you can go ahead and balance the equation. So technically, you would have a 3 here, and a 2 here, and a 6 right there. So if you wanted to balance it, just make sure it's like, well, how come I have a Ca3 here and I don't have a Ca3 here? Well, that's because, remember, the 3 is here because the phosphate has a -3 charge. Right? It doesn't have a 3 here because chloride has a -1 charge. Okay, so remember, writing formulas still is the same as what we learned a few months ago. All right, if you want to make them balanced, then you go ahead and do all the balancing. Okay, but what the trick is, oh, and then, well, we'll talk about this later, but what the trick is I kind of like to do this trick because, one, we will have to start doing equations that will include this. It's called a net ionic equation. So for those of you that watch the videos kind of know where I'm leading to. Okay? All right, why don't we do one more just to make sure. Let's do another one. Let's see. Let's do magnesium hydroxide. And I'll add that to, let's say, aluminum sulfate. Okay, and why don't you go ahead and write the ions down here. So this equation up here is called a molecular equation. What we're starting to write is what's called a complete ionic equation, because we're starting to show what's in the ionic form. Now, these are both aqueous. I haven't been writing it because I don't want to get too much stuff here, but these are both aqueous. So write, if you were to take magnesium hydroxide and if you dumped it into water, write what ions would form. If you took aluminum sulfate and you dumped it into water, write what the ions are. All right. This is called a beaker drawing. A lot of people find it more visual. If you want to do that, that's fine. Otherwise, if you want to do how I did, it's, you know, the ion plus an ion plus an ion plus an ion. So you can do it however you want. All right. So I'll give you guys a little bit more time. All right. Let's go ahead then. Okay. So the magnesium hydroxide. Magnesium has a 2+ charge. So Mg2+. And then hydroxide is one of the polyatomic ions. So you look on the polyatomic charge sheet, you'll see that hydroxide has a -1 charge. Okay, and I'm doing a beaker drawing, but if it's easier, you can just do it like this if you don't want to do the beakers. Again, I don't care either way you want. That's a minus. Yeah, we'll just do it up here. That's kind of nice. Magnesium 2+ plus a hydroxide. Now again, you don't have to balance this if you don't want to. The balance, I mean, if it helps you, if you're like, well, I have 2 hydroxides, where's the 2? A lot of people want to put the 2 right there. Okay, but remember, don't do that. I was telling you guys that you still have to write the formula correctly. Okay, if you just have to have that 2, the 2 goes here. All right, because I'm forming 2 OH minuses. All I'm showing here is what is this ion? What is the ion? The ion is not an OH2. This does not exist. OH2 minus ion. That does not exist. That's not a real ion. All right, it's just 2 hydroxides. That's what that 2 implies. Okay, the ion is just the hydroxide. That's what the ion is. You have to write just what the ion is. Here, aluminum. Aluminum has a 3+ charge, so you'll have a 3+. So I'll do the beaker drawing. And then you have a sulfate ion. And sulfate ion, if you look on the polyatomic chart sheet, is the SO4 with a 2- charge. And again, this 3 just implies I have 3 of these. Okay, I don't have an SO4 3 2- ion. Right? That does not exist. A lot of people do this. That's a common error that people do. Don't bring that 3 down. You have to make sure you understand what this 3 is. It just means I have 3 of these things. That's all that 3 is. It's not part of the formula. What I'm writing here are the actual ions that exists. Okay. So now your magnesium is going to pair up with your sulfate, right, to form magnesium sulfate. So it's a 2-to-2 ratio or a 1-to-1 ratio. So your formula for there is MgSO4. So magnesium sulfate. And then your aluminum is going to pair up with your hydroxide, so you need 3 hydroxides for every aluminum. So that formula is going to be AlOH3 would be the formula for that. Okay, so any questions on those? Isn't that good? Again, we're going to do a lot of practice. I also have a practice sheet, but the main thing that people get confused with is these numbers. What do you do with these numbers? Make sure you understand it. Again, if you're still not good at writing formulas and stuff like that, I highly recommend that you get good at that first so that you know that your formulas, because a lot of people here will put, like, I'll see this a lot, MgSO4 and then an Al2OH2. The reason is because they see the Mg has a 1 here and the sulfate has a 3, so they just take the Mg and the SO4 and pair it up. Well, that's not the right formula. You still have to do writing formulas correctly. Okay? So that's why I do this first. I draw the ions first. I do like the beaker drawings so that I know what the charges are on everything. Okay? So I have the correct charge, so I'll know how to write the formulas at the end. Okay, so that's the reasoning why I do that. Okay, let's move on. To go back to the original problem, we talked about, let's go back to this. Okay, so in this case, this is basically what we're doing. So the sodium iodide, the sodium pairs up with the nitrate. That's how we get NaNO3. And then the lead, which has a 2+ charge, pairs up with the iodine to give me the PbI2. And I'm forming a solid. Well, the question is, how do I predict which one of these is the solid? Is it the lead iodide or the sodium nitrate? Well, that's what this chart does for you. This chart helps you predict what is going to be soluble or what is going to be insoluble. All right, insoluble implies that's what the solid is. Okay, or the precipitate. Remember, these are precipitation type reactions. So shorthand for a precipitate is a PPT. PPT is shorthand for precipitate, because it's PPT. All right, so rather than writing out the whole word, I'll just put the PPT. Okay. So using this chart, you'll be able to predict which one is the solid. Okay, meaning it's the one that's insoluble, or you'll be able to figure out what is aqueous, which is soluble. That soluble implies it's still aqueous. Okay, so if you have your chart, if you actually printed it out, that'd be great. If not, you can just kind of remember this, but I'm going to kind of show you how to read this. A very simple way of reading it. Now, usually in 101, I don't have you memorize this. I'll supply this for you on the exam. Obviously, you'll be able to have it. But if you do take 111 or 112, you'll have to memorize this. Okay, so I'm just going to show you how to kind of do this, just so an easy way, so you have to, so it's easy to actually know. Okay, I drew a line between 4 and 5. The reason is because everything up here, 1 through 4, rule 1 through 4, anything that has these ions in it is always soluble. Usually I go over in class, I print this out for everybody, I have everybody write this, but I mean, you'll have it on the lecture video, but if you want to do it on your own, it helps you. So any molecule that has a lithium, a sodium, a potassium, an ammonium, an acetate, a nitrate, a chloride, a bromide, an iodide, or a sulfate is always soluble or aqueous. All right, notice, see, soluble, 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 soluble. They're all soluble. However, there are a few exceptions. So the exceptions means these now, anything with those with this, these are insoluble. Okay, or form a precipitate or a solid. Okay, so notice if you have a lithium, sodium, a potassium, ammonium, acetate, nitrate, there are no exceptions. Every single molecule that has one of these on it is completely soluble or aqueous. However, if you have a halogen or a sulfate, Notice if you have a silver, mercury, or lead. Silver, mercury, lead, lead. Silver, mercury, lead. So silver, which has a plus, mercury, which has a 2 plus, and lead, Pb 2 plus. They are insoluble. Same thing here. Silver, mercury, and lead. Insoluble. Sulfate, however, also has calcium, strontium, and barium. Okay, these are the metals in the 2A row. So if you have your periodic table, you can. So just to kind of show you a pattern. Notice these. Where is the lithium and the sodium and the potassium found in the periodic table? Right, group 1A. It's all of the 1A ions. Okay, so if you have like sodium iodide, that's going to be aqueous. If I have like sodium nitrate, that's going to be aqueous. All right, if I have like sodium whatever, it's aqueous. All right, same for lithium, same for potassium, same for ammonium. If I have a nitrate, if I have lead nitrate, Pb, and most lead compounds are insoluble. Pretty much every lead compound is insoluble with the exception of lead nitrate and lead acetate. Those are the only two lead molecules in the universe that are soluble in water. So lead nitrate is aqueous. Other than that, lead anything else is going to be a solid. All right, so you can see lead chloride, lead bromide, lead iodide, lead sulfate, even all these things, lead carbonate, lead phosphate, lead sulfide, lead whatever is insoluble. Only two exceptions exist. Okay? Does that make sense? There's a lot of writing over there. Down here, it's the exact opposite. Anything with these four are all insoluble. All right, I meant to put it down here. Insoluble. So notice everything here, insoluble, 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 insoluble. Okay? However, there's just a few exceptions where these are soluble, which we've already talked about. The group 1A, group 1A, group 1A, group 1A. What are the group 1As? And ammonium, ammonium, ammonium. It's this rule right here. This, all of this right here is the rule 1. Because I just told you, anything with these are soluble. It doesn't matter what you have. Otherwise, every other metal attached to a carbonate is completely insoluble. So chromium carbonate, magnesium carbonate, manganese carbonate, calcium carbonate, iron carbonate, tin carbonate, whatever carbonate you want is insoluble unless it's one of these four. That's what this rule is telling you. Okay? Same for the phosphate. All of them are insoluble unless it's attached to one of these four cations. Same thing for the sulfide. Same thing even for the hydroxide, except for ammonium. Ammonium hydroxide is not part of that. But all the group 1A, so sodium hydroxide, potassium hydroxide, lithium hydroxide. Then we're going to add 3 more, which are, again, our 2As, like how we saw up here, calcium, strontium, and barium. So these are all soluble. So if you go back to this problem, okay, we have a sodium iodide. That is aqueous. How do we know? Here, you know what? Let me erase all this. This is like so cluttered. Oop. Okay. So it's sodium iodide. So let's see why that would be aqueous. So it has a sodium in it. I don't have to go any further. It has a sodium, so I know it's going to be aqueous. All right. And then I have lead nitrate. Let's see. Nitrate, all nitrates are soluble. There are no exceptions. So this is aqueous, and this is aqueous. Now, let's look at our products. I formed lead iodide. Well, we just said all iodides are soluble unless it has a lead attached to it. See, that's one of the exceptions. Remember, this is lead, silver, or mercury. We aren't going to see any mercury compounds in this class, so it's pretty much it's lead and silver. Okay, so because of that one exception, that's what our solid is. That's the one that forms a solid. And then our sodium nitrate, since it has a sodium, which is soluble, also nitrate soluble, that will be aqueous as well. Okay, does that make sense as to how to read this chart? Yep, okay, good. Thanks, Holly. Okay, So let's just do a few problems. Let me get my notes. I have a bunch of problems in my notes. I don't want to, unless I have to think better for all of us. All right, let's see, chapter 10. Here we go. Let's do this one. Let's do. Let me. You know what? Let's do it on a this thing, because it writes a lot better. All right. So take sodium. Sodium phosphate, and this will be aqueous. Now, you always add two aqueous reagents. They have to be aqueous for this to react. And then aluminum sulfates. I guess we did that last time. This is kind of similar to what we did. That should be a 2. And SO4, 3. That's also aqueous. Actually, hold on. Aqueous? Yeah, all sulfates are aqueous, right? Yeah, okay. Except for those exceptions. Okay, so what I want you to do is I want you to draw what the two products are and then tell me which one is aqueous and which one is solid. So fill in the appropriate state that that molecule is in. Okay, and again, go ahead and do the part down here that I had you guys do, like the beaker drawing. If you want to make it as a beaker, I'm totally fine with that. And then just show me what the two products are. All right? I'll go on pause, and I'll let you guys do that. Let's do a different color. Let's use purple. Okay, so the sodium phosphate. So sodium phosphate is composed of a sodium ion. So sodium has a +1 charge. And then phosphate, if you look on the polyatomic charge sheet, has a PO4 3-. Right? Again, I'm just looking at the. I don't care about the 3 here because I just have 3 of these. Again, if you want to balance it, you'd put a 3 right there. That's where that 3 comes in. Aluminum, again, has a 3+ charge. We've seen aluminum a few times today already. And then sulfate, if you look on the polyatomic charge sheet, sulfate has a 2- charge. Again, if you want to balance it, you put a 2 here and you put a 3 here. But like I said, I'm not too worried about those right now. Okay, so now my sodium is going to pair up with the sulfate. So let's see, it's a 2-, so Na2SO4. All right, and if I go back to the solubility chart, let's see, anything with a sodium is going to be soluble, even if it's a sulfate. So I know that that one is going to be, this one is still going to be aqueous. Make sure you put aqueous, not S. A lot of times people put S. Oh, S means that it's soluble. Well, no, you have to remember down here, you know, AQ means soluble, S means solid. So you got to flip your brain like back and forth. I'm going to write down here, you probably can't see on your screen, but I have a whole bunch of windows right here. So that's why I'm going to put it down here. All right. And then the aluminum, which is a 3, pairs up with the phosphate, which is also 3. So that formula is AlPO4. So if we go to my solubility chart, I notice phosphates, all phosphates, all right, are insoluble, unless it's one of these 4 exceptions. Aluminum is not one of the exceptions, so that would be my solid. So that is the solid. So if I were to take sodium phosphate and aluminum sulfate, you know what? Why don't we actually do it? I'm sure it's on here. What is it? Aluminum, sodium sulfate. Sodium sulfate. For some reason, my typing is really slow in YouTube. Has anyone else found that? I know that my wife told me that she also has found that that when she types into YouTube on her computer, it's slow. I thought it was my computer, but I wonder if that's a. Has anyone else found that at all? I've already typed it. I'm waiting for it to fill in. You haven't? Yeah, isn't that strange? Man, I don't see how that would be a Wi-Fi I mean, that has to be a computer issue. But my wife's computer does the same thing, and her computer's a lot newer than mine. I mean, look at that. It's like thinking about how to type. Come on. I wonder if it's a Firefox thing. There it goes. Fractions between sodium sulfate and this barium chloride. Well, they might not even have it. After all that, they don't know how to do it. Of course not. Sodium sulfate. Well, let's do the barium chloride. This will be one. It'll basically be the same thing. So sodium sulfate. Here, let's do this. We'll do another practice problem. All right. So what was it? Sodium sulfate and barium. Sodium sulfate and barium chloride. All right. So sodium. I'll do it just so we can see. Sodium plus sulfate, and then barium has a 2+ charge because it's a 2A plus Cl minus. So the sodium pairs up with the Cl, NaCl. That's going to be aqueous because it has a sodium on it. And then barium sulfate, we said all sulfates, here let's go back to the solubility chart. This is kind of a good one. All sulfates are soluble, however barium sulfate is one of the exceptions. So it's going to be insoluble. That's what my solid is going to be. All right, so when you do the reaction, you should see a white precipitate. So here's the sodium sulfate down here. Barium chloride's added in, boom, immediately you get that white solid form. And then all of the sodium sulfate is still ionized in the water. You can't see it, but it's, you know, it's, so here's the problem. Barium sulfate is the solid, and the sodium chloride. All right. So there's, since we can't do lab, you'll actually just see it. Okay. There's another example. So let's finish this complete ionic equation. I need to make this smaller, so let me clear this. So sodium phosphate. I gotta write it smaller so I have room. Aqueous plus, what was it? Aluminum sulfate. 2, so 4, 3. Okay. So we did the Na plus the phosphate minus plus aluminum 3 plus the SO4 2 minus, and then we got sodium sulfate, which was aqueous, plus aluminum phosphate, which was a solid. Now, to complete this complete ionic equation, basically this equation down here is called the complete ionic. And what you're basically doing is showing what is still in the ionic form and what is in the solid form. So again, it's a beaker drawing. So imagine I have one beaker that has the sodium dissolved in it and the phosphate dissolved in it. And then I have another beaker that has the aluminum in it and the sulfate in it. And then I pour them together to get one big beaker. Well, what do I have in this beaker? Well, the aluminum phosphate is the solid at the bottom. All right, I'm going to put X's here to show you that it formed a solid. All right, and still ionized in the solution are the sodium ions and the sulfate ions. Those are still ionized. That is still soluble in the water. But the aluminum phosphate is not. That is a solid. So you show that in the complete ionic. You show the solid, the aluminum phosphate, has come all together, but the sodium sulfate is still in the ionic form. Okay? So that's basically a complete ionic. A complete ionic shows what's still aqueous. So anything aqueous is in the ionic form. So since my sodium sulfate is phosphate is aqueous, I write it in the ionic form. My aluminum sulfate is aqueous, so I write it in the ionic form. The sodium sulfate is aqueous, so I write it in the ionic form. And then my aluminum phosphate is solid, so it comes all together and is not ionic anymore. It's not in the ionic form. It's in the solid form. Okay? So that's what I'm showing in this equation. And then the final equation is what's called the net ionic equation. The net ionic equation basically shows the overall reaction. Okay? It eliminates what's called the spectator ions. Spectator ions are the ions that really don't do anything. They start in the ionic form and they end in the ionic form. So my spectator ions in this equation would be the sodium and the sulfate. Why is that? Because they're starting in the ionic form here, and they're ending exactly the same way in the ionic form. They have not changed. Okay? So since they start one way and they end exactly the same way, they're called our spectator ions. They aren't doing anything. They're just watching the action. So in the net ionic equation, I show what actually happens. So what actually happens is the aluminum and the phosphate, and you can write this in any order. It's not like you have to write it in the exact order, but you can put it however you want. The aluminum and the phosphate are starting ionic, and then they are changing their states because they are becoming solid now. So that's my net ionic equation. Basically, all the reaction is, all this fancy stuff, I have all this stuff, all that's really happening is the aluminum and the phosphate are joining up to form a solid. The sodium and the sulfate aren't changing. They actually stay exactly how they are. So that's the net ionic equation. It just shows you what's going on. Like when you get a paycheck, you have your net amount that you get. That's basically how much you get after they take all the taxes out and all the other stuff. It's just showing you what the overall deal is. Okay? So the spectators are the ones watching it. So it's kind of like us when we watch the Broncos lose. We're the spectators, right? And the Broncos are the ones who are playing it. And they usually lose. That's a joke. Well, it is, but not really, right? Okay. Anyways, a lot of these jokes go much better in live person. Obviously, it's hard to do on video when I don't know if you guys are laughing. But like I said, it's not like you laughed anyway, so it shouldn't matter. Okay, anyways. Any questions on net ionic or complete ionic? Thanks, Justin. Yeah, at least I'm trying, right? Okay, let's do another problem. This time I want you guys to do the whole entire thing. Do everything. So let's do this one. What's that one? Let's do potassium carbonate. Plus barium hydroxide. All right, let me just double check something real quick. Okay, good. Okay, so do the whole thing here. Finish the molecular compound. So this top one is called the molecular compound. It shows all the molecules. Then do the complete ionic. And then do the net ionic. Now, as far as balancing, if you want to balance every equation afterwards, that's fine. But I really just care about the net ionic equation. If you totally understand this, you're like, I don't have to balance it, that's fine. But if you want to balance the net ionic equation at the end. Okay? Okay, so the complete ionic, we're going to take the potassium carbonate, break it up into its components. So potassium plus carbonate ion. And then the barium hydroxide. Barium is a 2+ charge. It's in the 2A row. And hydroxide is one of the polyatomic ions. So it's a hydroxide. So the potassium is going to pair up with your hydroxide, give you KOH. All right, it has a potassium, which is one of the 1As, so we know that that should be aqueous. And then the barium is going to pair up with the carbonate to give me BaCO3, and that's what my solid is going to be. Because if you look here, carbonate, all carbonates are insoluble. So this row right here, all carbonates are insoluble. All right, with the exception of these, which is not one of the exceptions in our product. All right, so to complete my complete ionic equation, this is still aqueous, so we're going to keep it aqueous, calcium hydroxide. And then my barium carbonate is a solid, barium carbonate. That's a solid. All right, so my spectator ions is the potassium and the hydroxide. I sometimes will cross them out just because, so I can see what's left over. So with whatever's left over, so barium plus carbonate. And again, you can write this in any order. A lot of people say, what orders have to be written? You can write it in any order you want, as long as you have the correct ions and molecules in there. Solid. Okay, so I mean, all I'm doing is everything that has been crossed off. So the carbonate is coming down, the barium's coming down, and then on the other side of the equation, the barium carbonate's coming down. It's already balanced. It's a 1-to-1, so you don't really have to balance it anymore at that point. Okay, if you wanted to balance the one up here, you would just put a 2 right there, right? Because you should have 2 calciums and 2 hydroxides. Form 2 calciums and 2 hydroxides. So that has everything balanced. But again, I don't care if you do this balancing up here, but it's just the net ionic equation. Okay? Any questions on that? Oh, I don't have your chat up. There you go. Okay? Good?
Justin, will the homework require us to balance the equations?
That's a good question. I'm going to say yes, because I don't remember what the questions have. So you should still know how to do it. But when I give exams and stuff, you don't really have to worry about it. But yeah, the homework might have you do that.
Okay.
Yeah, that's a good question. Let's see, Holly asks, do we balance the amount of ions? Yeah, I think I understand what you're saying. It's just, you know, if this final problem had like a 3 right here, let's just say, you would put a 3 right there. That's pretty much it. Okay, yep, no problem. Okay. Good. Anything else on these? You guys want to do another one? I have no problem in doing a few of these practice problems. So I'll make sure you get this, because it's one of those things that it's a lot of stuff that's going on. Okay, Justin said yeah, no problem. So I have tons of practice ones. I do want to get into another type of a double replacement, so let's do one more, and then we'll talk about this one last one, and that will probably be it for today. And then tomorrow, we'll do more of these practice problems. I'm almost debating to continuing lecture tomorrow, but yeah, I think we'll just finish it next week. All right, let's see what was going on. Let's see if it counts. Let me just look something real quick. Okay. Again, do the whole thing. Molecular equation, net ionic equation, complete ionic equation. Okay, so potassium plus sulfide, iron plus chloride. So we will get potassium chloride. It's Potassium pairs up with the chlorine. That will be aqueous, because it's potassium. It's also chlorine. And then iron sulfide. So Fe2S3. I'm assuming that's the solid, but let's double check. So sulfides, all sulfides right here. This is the rule right there. So all sulfides are insoluble unless it's a lithium, sodium, potassium, or ammonium, which it is not. So that would be the solid. So potassium and the chlorine are ionic. And the iron sulfide is the solid. So the spectators are the potassium and the chlorine, and then whatever's left over. So let's take the iron. I just like to put the cation first, just because that's how we write the formula. But if you put S2 here and iron there, that's fine. I just like to do it just so, because when I write my formula, I write it like that. Now in this case, we will balance it, so you would put a 2 here, and you would put a 3 right there. Let's get it right into it. All right. So that would be the net ionic equation. That good? All right. So notice I have the ions balanced, but also what happens is our charges are balanced as well. All right. Notice 2 times 3, that gives me a 6 plus. 3 times minus 2 gives me a minus 6 for overall of 0. And the overall charge of this molecule is 0. So that also is balanced as well. So I see a Y. Y for what? Andrew, if you want to go off your mic and tell me. I'm not sure.
I was just wondering why you're balancing this one.
So yeah, so I was saying the only one I care about that you balance is the net ionic equation, just to kind of show the overall balancing. If you want to balance these, that's totally fine. But really, the answer of these problems is this right here, is our net ionic equation. So that's kind of the one where you just do everything on that one. All right. Does that make sense?
Yeah.
Okay. You know, I mean, if you want to balance this one up here, let's do it a different color just so we can see the difference. So like 2 potassiums, you would have a 2 here. And then, let's see, you have, well, you know what, let's do, this is actually a good example as to why you do the largest one first. So we talked about this yesterday. First, look for the formula that has the most ions, which are atoms, which would be this one. And the sulfur, there's 3. So let's do there, 3. And then the iron has 2. So that gives me 6 potassiums, 6 chlorines, and 6 chlorines. So that would be my balanced overall equation at the end. So if you look, that would be 6 here. You'd have a 3 here. You'd have a 2 here. And you have a 6 here. So 6, 6. So you're 6 chlorines, and you have 6 chlorides, 6 potassium, 6 potassium. And then notice you have 3 sulfides. Give you the 3 sulfides, 2 irons, 2 irons. And then that has a 1. So it gives you 1. So I mean, if you look, I mean, you can balance them all. It all follows. But if you don't want to take time in doing the balancing, I totally understand. If you would rather do it because it makes sense, that's fine also. But that's why I just care about at the very end. You just balance at the end. Okay? Okay. So the next thing I want to talk about, where's my... Did I close these slides? Oh, I closed the slides. Let's see, do I have slides over here? So the last thing I want to talk about for today is complete ionic. So I'm just going to show you the slides, everything we talked about. Here's the complete and the net ionic equations. We talked about that. Here's how to do them. Write a molecular equation, predict the products, do the complete ionic, do the net ionic. This is just an example problem. And here's some more problems. So I want to talk about this, which is called an acid-base reaction. This is also a type of a double replacement reaction. Let me just see what there is. Okay. So For double replacement reactions, there are two types. So for a double replacement, there are two types. And the first one is a precipitation. It's exactly what we've been doing. But a second type is a acid-base neutralization. Acid-base neutralization. That's a second type of a double replacement reaction. Okay, so notice up here I have an acid, I have hydrochloric acid, and I have a base. You still do a double replacement reaction. The cation here, which in this case will be the H+, pairs up with the hydroxide. And you form HOH, which, what is HOH also known as? H2O, water. And the sodium pairs up with the chlorine, which is the sodium chloride, which is salt. So notice, if you take an acid and you add it to a base, you basically form salt water. So notice I neutralized my acids and bases. Like if you talk about pHs, here I have a pH, of a 2, and here I have a pH of about 12. And when I add them together, I get water and salt, which all have a pH of 7. Well, salt doesn't really have a pH, but water is a pH of 7. So I basically have neutralized my acid or my base. So in lab, if you actually spill an acid, if you have an acid spill, you actually clean it up with a base. You basically add base until it's neutralized, and then you clean it up. Or if you spill a base in lab, then you grab an acid and you neutralize that base until you get a pH of 7, and you clean it up. All right? So it's still a type of a double replacement reaction where the cation here pairs up with the anion here. But in this case, because we're using an acid and a base, I don't form a precipitate. All right? I form water, which notice is a liquid in this case. It's not an aqueous or a solid or a gas. It's a liquid. Okay? So it's the same type of a reaction as that we've been doing. Everything's been identical. Let me just get this real quick. It's a lot easier to write on here. So you have your acid, which in this case HCl, plus you take sodium hydroxide, all right, and you do a double. So again, in order to do the complete ionic, so hydrochloric acid breaks apart into H+ ions and Cl- ions. All right, if you remember, what makes an acid is H+ ions. And then this, the sodium hydroxide, breaks down to sodium ions plus a hydroxide ion. So the H pairs up with the hydroxide to form H2O, which in this case is a liquid. Liquids do not ionize. And then the sodium pairs up with the chlorine, and if you go on the solubility chart again, you'll know that sodium chloride is aqueous. So in this case, your complete ionic, water is a liquid. It's not ionic. So you treat it as if it was like the precipitate. You write it as the actual formula. And then sodium chloride is still ionic. So anytime it's aqueous, you write ionic. If it's anything other than aqueous, if it's a liquid, if it's a gas, if it's a solid, then you write it as the whole formula. So my spectator ions, again, in this case, is the sodium and the chloride, because those start ionic and they end ionic. So the overall reaction, my net ionic equation, is H+, which is acid, plus my hydroxide, which is base, becomes water. It neutralizes. That's why this is called a neutralization reaction. I take an acid, I take a base, add them together, and you get a neutral molecule. So it's still a double replacement reaction. However, it's a different type of product in this case. In this case, this is usually going to be my net ionic equation. Okay, so why don't we just do one of these, do the same exact thing. I'll give you different acids and bases. Let me give you sulfuric acid, and let's say we have, let me just look at something real quick. Let's say calcium hydroxide. Okay, so do the whole thing for that, the complete ionic, the net ionic, all that stuff. I'll give you maybe like 5 minutes because we're about the end of the class for today. All right. All right, I'm gonna start going over it because I also forgot I want to answer Holly's question as well. All right, so I want to explain. I'll just write it down, so you guys, if you guys are still working on it, you can go ahead and still work on it. Oh, that forms a solid, doesn't it? Yikes. All right, let's keep it a solid. I'll show you what you do in that case. This can happen. So in this case, your net ionic equation is the same as your complete ionic equation. You actually form water because your H plus and your hydroxide neutralize each other, but then you also form a precipitate. So if you're net ionic, in this case, you do not have any spectator ions. Everything reacts, and that is a possibility. So I didn't want to write a problem like that, but it does happen. So. All right. And this usually just happens in acid-base reactions where you won't have spectator ions, where you form a precipitate as well as your water. But if you have, but in other cases it won't happen. But I'm okay that happens. Just going to show you that it can happen. Okay, that makes sense. Hopefully you guys got that. All right, any questions? Otherwise, I'll transfer it over to Holly to see what her question was for Chapter 8. All right, Holly, what was your question? If you want to go off speaker, that might be easier. This way you can just tell me. Oh, you can't speak right now. Okay. All right. Then why don't you just go ahead and type in what the question is. Go ahead. In the homework, it asks what is soluble in water on one question and what is most soluble as a pair. So that question, it depends exactly what the question is, but it might be referring to this chart. This chart, they talk about in Chapter 9. Now, I didn't talk about it in Chapter 9 because I wait for it in Chapter 10, but they do talk about this in Chapter 9. So that question might be referring to this. But if you can get, because if it says on the homework, it asks what is soluble in water. So these, again, is based off of our solubility rules. And what is most soluble as a pair. So again, like the questions that we've been having, there are some that are aqueous. So if I give you a pair of like lithium hydroxide and, I don't know, chromium phosphate, obviously the chromium phosphate is insoluble, but the lithium hydroxide is more is soluble. So that's probably what they're talking about. If you can give me an exact example, that would be better. But does that sound like it would probably be it now after in discussing this? Yeah, it gave options and asked to tick what is soluble in water. The pairs were asked if a CH something is insoluble in wet. So yeah, so this probably has to do with when we talk about the inner molecular forces. So something that has hydrogen bonding is also soluble in something else that has hydrogen bonding. If you just have a molecule that just has carbons and hydrogens, that's very nonpolar. So that would be van der Waals forces. So that would be soluble in something else that also has just van der Waals forces. So there are two types of way of answering it now. One, if it's an ionic molecule, you are going to use this chart. All right, so that whole thing. But if it's not ionic, if it's just a bunch of carbons and hydrogens, and and if you have hydrogen bonding, we talked about that a few chapters ago, then something that's very polar or has hydrogen bonding is also soluble in something that's polar or has hydrogen bonding. But if something is very nonpolar, like again, if you have a molecule that is just a bunch of carbons and hydrogens, so if you have something that's just all carbons and hydrogens, this is very nonpolar. So if it's nonpolar, it's soluble in something nonpolar. It goes back to what we talked about: like dissolves like. That's that saying that we talked about: like dissolves like. So that basically means nonpolar things dissolve nonpolar things, or polar dissolves polar. So, like for example, water will dissolve methanol. All right, because there's a hydrogen bond right here. You remember, hydrogen bonding is between hydrogen oxygen, hydrogen nitrogen, and hydrogen fluorine. So this has hydrogen bonding, this has hydrogen bonding, therefore these are soluble in each other. All right, but if I took methane and water, this has hydrogen bonding, all right, but this has van der Waals forces, or the dispersion forces, I guess is how we talked about it. So since these are not the same type, these would be insoluble in each other. Because you have something that's very nonpolar, and you have something very polar. And remember, it's like it dissolves like, but here I have nonpolar versus polar. These would not be soluble. Okay? So it depends if they're asking about this type of question, or if they talk about this type of question. So there are two ways that you have to look at it. If it's an ionic molecule, you're going to look at this chart. All right. If you have non-ionic molecules, then you'll have to think about this, the like dissolves like. Okay, so hopefully that helps. So are all the things on the chart soluble in water? Well, no. So this chart we talked about already in class, right? So we talked about, so I had you, like, I'll draw the line. These things are soluble. Here are the exceptions. So everything that we learned about still applies. So no, that's not true. It's not everything here is soluble. You still have to look at what we did in class. Okay? But all the things that are soluble in water. But all the things that are soluble. Well, yeah, if it is soluble, yes, it's soluble in water. Unless it's a compound that is insoluble in water. Like if it's silver chloride, that would be insoluble in water. Or if it's any one of these things, then it would be insoluble in water. So yeah, right, yeah. So yeah, okay. I think I understand your question. Yeah, all of these compounds refer to water as our solvent. We're just assuming water is our solvent. So yeah, so if I say the word soluble, it's always implying in water. All we're talking about is water. I think that's what your question was. Yeah, okay, yeah. Yep, exactly. So yes, it's always water. Yeah, because when we say aqueous means water. Aqueous, I think, was like Latin or Greek for the word water. So yeah, if we say aqueous, it implies water. Yep. All right, good. Yep, no problem. Any other questions? Otherwise, we'll call that a day. So tomorrow we will go over some more problems. If you guys have more questions, we'll do those. And that's pretty much it. All right. Otherwise, I'll see you guys next Tuesday.
All right, thanks, Steve.
Yep, no problem. Pete, have a good day.
Enjoy your brisket.
Yeah, no problem. I definitely will. I think we'll enjoy that for like a week. It was like a 16-pound brisket. So
you can chop some up and you can put it in. You can have it with eggs for breakfast. Sandwiches for lunch.
For like every meal. Yeah. I'll put like ice cream and hot sauce over it too.
Perfect. All right, see you.
All right, bye guys.